All right, everyone. Hello, welcome back. So as promised, next we will talk about gravitational potential energy and another type of mechanical energy you'll see here. In the next recording, I will talk about the last one here, which is the spring mass. All right, so what exactly is gravitational potential energy? Well, it's energy which is in a sense stored in an object which just depends on its position relative to the surface of the earth. So the indicator for gravitational potential energy, and we simplify that, write it as PE subscript G for gravity. So the indicator is height. So you know that you need to do work in order to take a heavy object and lift it up. So the higher you lift it, the more work you're doing. So as we talked in the last recording, when we saw that we needed to do work in order to give something motion. So likewise here, we need to do work in order to give an object this gravitational potential energy. So it just has to do with its position. The word potential, you could think about it as it's the potential of that object to have kinetic energy. Because what happens is when you lift an object up, in a sense, you're storing this gravitational potential energy because the moment you release it, that energy will get converted to kinetic energy. And the higher the object is, the more kinetic energy it will gain as it falls down. So we'll look at many such examples. But let's start by just thinking about this one example of a physical system. So now in a physical system, we do have to, whenever we're talking about gravitational potential energy, we have to include the object whose potential energy is changing plus the earth. And the reason is that it's exactly that interaction between the object and the earth that's giving it that gravitational potential energy. If you were in outer space, far away from any effects of gravity, then it would not require any work to move an object in any direction. So it's really that interaction between the box and the earth. The earth wants to pull the box back down. So it's that force between them that's giving it its gravitational potential energy. All right, so let's look at this interval where initially, let's just define the initial height of the box at 0. We will talk in more detail later about the exact meaning of height, but for now, let's just assume that it doesn't matter where we define it to be 0, which turns out to be true. So let's just say that initially it's at the floor at the height of 0, and then you lift it to some final height, which is not 0. And then you assume that in this interval, the speed doesn't change. So initially it's stationary, you lift it. The final state is you're holding it at a bigger height, it's also stationary. So the key here is what really matters is what are your indicators at the start and at the end of your interval. Yes, sure, the box was moving in between as you're lifting it, but it doesn't matter. You only care about a time equals to 0 at the final time. What are the speeds? And we're assuming it's stationary. So the only energy that's involved here is this gravitational potential energy. It's increasing because the height is increasing. That's its indicator. What does that tell us? Well, if the total energy is going up, then there's again no heat involved here. You're not heating up the box, which is letting it go up. So it has to be work. If this is positive, work is positive, that means that you're doing work on the system. What is the equation for gravitational potential energy? It's proportional to the mass. So the heavier the object is, the more work you would need to do to lift it a certain height. Then it's proportional to this gravitational constant. It's the acceleration due to gravity. It's actually exactly 9.8, but for simplicity in this class, we often just let you round it to 10. It doesn't result in a very big error, and it's just an easier number to work with. So in 7a, just kind of accept the fact that we tend to use 10. It has units of meters per second squared, and then it's proportional to height. And you see here that the sign will matter. If you're moving up, that's going to be a positive change in gravitational potential energy. If you're moving down, that's going to be a negative change. So here we have a positive change resulting in positive work. So you're exerting a force on the box in the direction that it's moving, which gives it positive work. All right. So the question is, again, how much work? So we kind of did a fun calculation in the last recording where we saw how many calories did it take for a baseball player to throw a ball. Now let's think about gravitational potential energy. We can do a similar calculation, but now let's assume that we know that the energy we want to spend. So let's say you drank a 12-ounce can of soda. And the question is, how many flights of stairs can you climb using the energy that you get from this can of soda? Okay, so 12 ounces of soda has 1/4 of a cup of sugar. That might make you reconsider drinking soda ever again. That's a lot, which translates to 160 food calories or 680 kilojoules of energy. All right. Now let's use that fact that our body is about 25% efficient. So not all of these calories are going to go into your ability to work. Some of it, they're just going to be converted to heat and be used up to making your body internally function. So the amount of work, let's say you have available, is 25% or 1/4 of this 680 kilojoules, which is 170 kilojoules. And then the work will be the change in gravitational potential energy as you move up the stairs. So what we really want to calculate is, given this amount of energy that's available to us, how high can you go? Let's assume kind of a standard, mass for a person, 150 pounds, which converts to 68 kilograms. So you plug in that for mass. Remember, this equals to mg delta H. In this case, we use Y. It doesn't matter what variable you use. So you plug in 68 kilograms here. This is 10. And then you divide 170 by that, by 680 that you get. And this is kilojoules, so you have to multiply by 1,000. So you do all the math and you find it's about 250 meters. So what does that tell us? That converts, if each flight of stairs is about 2.7 meters ballpark, a story of stairs, that converts to about 94 flights. So that's about the height of an Empire State Building. So it's pretty impressive that with a can of soda, you can go that high. Of course, this calculation is not perfect because you're not only moving up, you're kind of moving horizontally, and then you're doing work against friction too. So, the actual calculation gets a little bit more complicated than this, but it's an okay ballpark calculation of how much energy is required to fight against gravity in a sense. All right, let's look at another example. And now we're going to kind of combine the ideas of gravitational potential energy and kinetic energy. So now let's look at an example where initially you're holding a ball at some initial height, let's call it h naught, and initially the speed is 0, and then you let it go. So the instant you let it go, it's still not moving, that very instant. So its initial speed is 0. And let's look at the final state or time in our interval is right before this ball hits the ground. And let's call the ground's height 0, but then the speed is not going to be 0. We very much so know that this ball is going to move down and speed up. So here we have a change in kinetic energy. Now, what's in our physical system? We have the ball and the earth. So whenever it's a little bit harder when we talk about mechanical energies to decide whether a system is open or closed. With thermal energies, we just said, okay, if things are in a thermally insulated container, which is closed, we say it's a closed system. Here we have to think about, is there anything else which is interacting with the ball and the earth? So you might think, well, this girl is interacting, but you have to think about, is she interacting with the ball during this interval? So remember, our initial state is the moment she lets go of the ball. So she's no longer holding the ball, so she's not exerting any force on it. In this interval, she's no longer interacting with the ball. Then also, our final state is right before it hits the ground, so the ball is not interacting with the ground either. It will eventually, but we just want to focus at the ball's energy in this interval as it's falling. So if there's nothing else, then we can assume it's a closed system. There's of course air, and air has some effects of friction, and we'll talk about the importance of friction when analyzing mechanical systems in the next couple of recordings. So maybe not the next one, but the one after, I'll discuss that. But for now, we're neglecting any effects of friction. Okay, so how would this energy interaction diagram look like? Well, we know that the height of the ball is decreasing, so gravitational potential energy goes down from initial height to 0. And we know that kinetic energy goes up. Even if we didn't know that, this tells us, energy conservation tells us that if we have a closed system where one energy goes down, the other energy has to go up. So the ball speeds up. How does that look? Because it's a closed system, the right-hand side of the equation is 0. We have two energies changing. We have kinetic energy and gravitational potential energy. If we take it a step farther, since our initial is 0, this just ends up being 1/2 mv final squared. This is the positive value. Now here we go from 0, that's our initial. So you would write 0 minus the final, which is, no, sorry. So our initial height is h0, the final is 0, and we always do final. This delta means final minus initial, so it's 0 minus h0, so that's why you have this minus sign appearing here. Sorry if I confused you there, kind of confused myself. Okay, so again, it's always important when you're writing down these energy conservation equations to check signs to make sure it makes sense. So we have here a quantity which is clearly positive. We have here quantity which is negative. So equal and opposite. All the potential, gravitational potential energy gets converted to the kinetic energy of the ball as it moves down. Okay, so now I will let you think of some examples where we have specifically a transfer between gravitational potential energy and kinetic energy. So imagine a bowling ball attached to a rope, attached to a ceiling. So it's kind of a strange situation, but actually it's a demonstration that I do in lecture when we have lecture in person. Kind of a fun one. So imagine this bowling ball is released from point A. So you take it, you move it up, and you let it go. What's going to happen? It's going to swing this way. So it's going to go from point A to this position to C, and then back to A, and so on. So let's think about it in terms of energy. So first, I want to ask you, when is the gravitational potential energy of this ball maximum? So your choices are at point B when it's vertical, at A only, at both A and C, or maybe somewhere in between, none of the above. So think about this. Go back to the definition of gravitational potential energy if you don't quite remember, and then pause the video and answer. Let's look if you got it right. Oops. So The answer is at both points A and C. So this is when the bowling ball will be at its maximum height. It might not be completely clear to you that E will return back to its maximum height at point C. So again, remember, at this point, we're neglecting any effects of friction like air friction. So really, we are assuming that the only energies that are present here are kinetic and potential energies. So if we start at point A with some initial energy, remember it was just released, you didn't push it, it's all potential energy here, so it has to be the same potential energy at point C at the maximum height when it turns back around. We're going to look at this in more detail after the series of questions for you. Okay, so same situation. Now I just want to ask you, when is the speed maximum? So think about this. So the speed is going to be maximum at point B when the ball is in this vertical position. So why is that? So again, what is happening here is that you initially have all potential energy. As the ball swings, the potential energy decreases, and what's increasing? Kinetic energy, until the potential energy reaches its minimum value here. So that should tell you when the potential energy is the smallest, the kinetic energy is going to have that biggest change, biggest value here. And then what happens? It continues swinging. Now it's gaining potential energy again, which means it has to start losing kinetic energy. So here it's maximum. So another way that we can look at conservation of energy is, instead of thinking about how energy changes, we can think about the total energy of that system. So another way of basically rewriting this equation, what is this delta total energy, is just the final minus the initial. So if you move this to this side of the equation, and this is just, of course, true for a closed system when the right-hand side equals to 0. So then you can rewrite this as the total energy of some final state equals to the total energy of some initial state. What does that tell us? That in any interval that we choose, whatever your initial or final value is, so if we go back, it could be from point A to B, or from B to C, or from somewhere in between here to in between there, any two locations, this is always going to be true. So what that tells us is that the total energy is going to be a constant. It's going to be the same at all of these values. So for example, for the bowling ball, what is our total energy of this closed system is the gravitational and the potential energy. So it's the sum of these two that's going to stay the same throughout its whole motion. Of course, from everyday experience, we know that if we let this bowling ball swing, eventually it will stop. And why does it stop? Well, that has to do with friction. So we're not quite getting there yet. For now, we're just assuming in the short interval, all this energy is conserved. So it's a closed system. Okay, so let's kind of look at this now in terms of total energy. So we know that at some initial location A, so here's kind of we're defining here our 0 height when the bowling ball is going to be at our minimum value. So initially we have just gravitational potential energy because the ball is stationary, you're holding it, and it's the moment you release it, it's still stationary. So the total energy is going to be gravitational potential energy. And the way that I'm going to kind of depict this total energy staying constant is by imagining we have some kind of bucket filled with energy, and blue will be potential energy. So at some later time, let's say when the ball is in this position I'm calling B, now the ball is moving, but it still has potential, gravitational potential energy, because it hasn't reached its minimum height, which we're defining as 0. So let's assume that at that particular location, it's exactly half and half, but it has to be conserved. So the total amount of energy, so like how far this bucket is filled, has to be the same between points A and B. Now it's just half of that potential energy has been converted to kinetic energy. Now when we're going to point C, now it's all kinetic energy because we reached this value, which we defined to be 0. Remember, the indicator of gravitational potential energy is height. Wherever we define it to be 0, that's when that energy is going to be 0. So now it's all kinetic, but still the same amount. So all of that potential energy got converted to kinetic. And then, eventually, as we go back up, again, it gets converted to potential energy. So this is why the height at this initial location compared to its final location before it turns around has to be the same, because you have to get back the same amount of potential energy. And what basically this tells us, conservation of energy, another way of writing it is that the total energy at all these locations has to be the same. It's a constant. So there will be two ways that we will be from now on kind of thinking about conservation of energy in terms of how it changes from some point A to B versus what is the value of the total energy. These concepts are gonna especially be useful to us when we start graphing energies, which we will do in a week or so. All right. So again, to summarize, for closed system, total energy is constant, and it's really an identical statement to saying that the change of the total energy in any given interval, as long as that system is closed, is 0. All right, I have one more question for you here. So imagine Bob, and he's sliding down this ramp. So there's this ramp, and then eventually it ends and he keeps on flying up. So let's focus in this interval. So initially the speed is 0, so right before he starts sliding. And then at this final interval that we want to look at, Bob is still flying with some given speed. So the question is, what's the maximum altitude can Bob reach during this motion at this location? So imagine initially we have some initial height, y sub I for initial, and if you do a dashed line, yb would be the same height. So the question is, at this location, is Bob lower than his initial height, at the same height, or possibly higher? So think about this. Again, use concepts of conservation energy to answer this. All right, so the answer is that the height at this time in the interval is going to be lower than the initial height. So let's think about why that is, because if you are thinking about it in terms of the pendulum that we just did previously, or the bowling ball, we saw that height as the bowling ball was swinging was the same. But this situation is different, because here Bob has some kinetic energy at this location. It's not that it's some kind of swinging motion where he's turning around, he's moving here. So initially, his total energy is just this gravitational potential energy, which is mgy, right? There's no kinetic energy. But now at this location that we want to look at, he has kinetic energy. So he has some 1/2 mv final squared kinetic energy, but then there's also potential energy. I call max, I say this max because we're just, we're assuming that this is like the maximum height that he's going to reach. So if we compare this value has to be the same as this value. So if the answer, let's say, was B, what's the only way he could reach that same height as the initial if there was no kinetic energy? This kinetic energy adds a value. Remember, we're trying to keep energy constant. So what that means is that mgy has to equal to everything here. So again, if he reached the same height, then that would tell us that this has to be 0, but we know that that's not true. And of course, the same is true for height, which is higher. If this was higher, then of course we would have a total energy here, which is much greater than his initial total energy, but he cannot be gaining energy out of thin air. So that means that these two, in order for these to be to be the same, this term, the gravitational potential energy term, has to be less exactly by that value of kinetic energy than the initial gravitational potential energy. So at this point, then his height has to be lower than the initial, which is YC. All right, thank you for listening. See you next time. We will talk about spring mass potential energy in the next recording.